SwayamPrabha. Digital India. Educated India.
Last two lectures we studied gyroscopic effect on the critical speed or whirl frequency of the rotor system. In fact, those two lectures were slightly special case, like when we considered the cantilever rotor system with a thin disc or long stick. We considered a very special case of whirl motion, that is synchronous whirl condition. In that particular condition, we were that is the definition of the critical speed. So, basically we were looking for with such analysis to find out the critical speed. So, as such the whirl frequency we did not consider during that lecture. Also we considered in some restrictive way the pure tilting motion or wobbling motion of a motor shaft disc assembly. In that particular case, we relaxed this particular condition of synchronous whirl and we obtained the whirl frequency variation with respect to speed. So, in previous lectures basically we did not consider the general motion of a disc, that means both translatory as well as the wobbling motion or tilting motion along with the asynchronous whirl. So, that particular case we did not consider till now, and today we will consider that particular case in which we will take an example of a cantilever shaft attached with a thin disc at the free end, and we will analyze a synchronous whirl condition, and we will try to find out how the whirl frequency changes with the spin speed of the shaft. Also then from Campbell diagram we can able to obtain the critical speed of the shaft system. So, this is the overview of the present lecture, in which we will be doing the analysis of a cantilever rotor with a thin disc for asynchronous motion. In this particular case, we will be considering both translatory and the wobbling motion of the disc. Effect of gyroscopic couple on the whirl frequency will analyze. Some of the concept which we will be covering in this particular lecture is like general asynchronous whirl motion, forward and backward critical speeds, disc and elastic coupling effects on the whirl frequency. These are the analysis we will be doing. So, for the present case we will be considering a cantilever beam like this, and this beam not only it will be spinning about its own axis, this shaft will be spinning, also it will be whirling, and in this is the whirling motion. So, spinning and whirling both will take place, and in this particular case we will consider the spins and the whirl frequency different, and we will try to see how this whirl frequency changes with the speed. In this particular case again we will not consider the there is unbalance in the rotor. So, this will be a free vibration analysis, and will in this particular case, because asynchronous motion is not there, which synchronous motion is not there in that, but in previous case we considered that, and we saw that when this particular shaft bends and whirls in synchronous condition, the fibers of this shaft which is in tension always remain in tension, and which is in compression it remains in compression. So, for this particular case that will not be there, fiber will during the whirling it will be changing its tension or compression stresses. So, let us consider the cantilever shaft with a free disc at the end. Because this particular case we have spin of the shaft about its own axis, and this is the bearing axis, and this itself is having whirling with different frequency. So, if we want to analyze the motion of the disc, as such, if both the spinning and whirling is there, it is very difficult to visualize the motion of the disc. So, in this particular case we will consider two cases, one in which we will be considering pure spinning of the shaft. So, let us say at this extreme position of the bend of the shaft it is spinning, but there is no whirling. So, whirling is not there. So, I am putting this as 0, and another case will be pure whirling. So, in this particular case shaft is not spinning, only the pure whirling is taking place. So, is moving along this path with frequency nu, but as such there is no spinning, spinning is 0. So, this particular case is, we call it as pure whirling, and this particular case is pure spinning. So, in this particular case the first one, when the pure spinning is there, if you see the angular momentum of the disc will be in this direction and value will be IP omega. So, for the pure spinning case angular momentum is straightforward, it will be tangent to the shaft at this location. So, if we draw a tangent from the shaft, it will be something like this. But for pure whirling case the calculation of the angular momentum is slightly difficult. So, we will try to see the motion of the disc during whirling, how it tilts, and then we will calculate the angular momentum of this particular disc due to pure whirling. So, for pure whirling, let us try to see the motion of the disc, how it take place. So, this is the bearing axis, let us say this is the bent shaft, there is a disc here. Now, as I told, the motion of the disc is slightly difficult for this case. So, we will take a small shaft segment here, let us say of length ds, which is attached to the disc, very close to the disc, and we will try to see the motion of this particular shaft segment, this one. This particular shaft segment, if we extend, so that is nothing but a tangent to the shaft at the bearing location. So, we will see that this particular shaft segment will make a conical shape about the center, let us say A. So, this is the whirling direction nu. If you want to see the motion of the disc when it is going from this bottommost to the let us say at the bottommost the time is t is equal to 0. So, at a time t is equal to, after some time delta t, where this particular disc will go. Okay. So, in this particular case, let us visualize the motion of the disc. So, is not spinning, only the whirling we are considering. So, this is at the bottommost position. Now, if I am considering the motion of the disc during whirling, you will see that earlier you could able to see only a line of the disc, but when it is whirling, when it is inside towards me, you can able to see the inside face of the disc. But once it comes to the top, again you will see the disk as a straight line, but when it comes out towards the U, then you will see the outside plane of the disk. So earlier when it was here, we could able to see the inside side of the disk, and here we are seeing this particular side of the disk. So basically this particular disk is tilting about its diameter during the whirling, and now again we will consider, let us say, from this bottommost position. So when it is coming this side, so you can able to see basically it is trying to tilt about this particular diameter, which is a vertical diameter. See, this is tilting at this particular instant about a diameter which is this diameter. So let us say when we are looking from this side, the whirling direction is counterclockwise direction. So when after some time the disk will reach from this bottom position, which is C, to, let us say, a position which is C prime. So that will be inside the screen. So this C prime will be inside the screen, and this particular disk will be tilting about its diameter here. And if we see the tilting direction, tilting direction will be a vector which will be this side. If we use the right hand rule, the tilting direction will be this side. So this we can able to visualize better from here. So when it is going this side, you can able to see it's tilting about its diameter with this, so upward direction. Okay. So basically we can able to this particular motion which we are considering is for very small time duration, from 0 time to delta t time, and for that particular instant of time this disk will be tilting about its diameter here. And now we will see how we can able to get the angular momentum because of this tilt of the disk. So again I am drawing the motion of the disk. So initially it was here, and then after time t it reaches to C prime. Because the whirl frequency is v, the angular velocity of the whirl is v nu. So this particular angle will be given us, because we know that if you see here, we have this as y displacement, and the tilt of the disk is, let us say, phi x, when we have axis system as this as z and this as y. So tilting of the disk is given by phi x, and the translatory displacement of the disk is y. So we will be having this particular angle will be nu into delta time t. So this is the angle which will be traversing the disk from C to C prime. this is the center of the bearing and this is the distance y. So, the C prime will be y and the angle nu t. And if we want the C prime divided by AC is the this is the apex of the cone. So, A to C, this can be written as nu y dt, which is this is coming from the above expression, and AC, this can be written as nu y by AC into dt. Now, y by AC is y is this distance, AC is this. So, we have this particular angle which is basically tilt of the disc as phi x. So, y by AC is phi x. So, nu phi x dt. So, this ratio becomes nu phi x and dt. If we see this particular A point here, there is a line AC, this one, and there is another line AC prime. So, you see in this particular delta time t, the change of the angle of the AC and AC prime, this particular angle is basically C prime by AC. This is the angle which we have obtained, CC prime and AC. This is the angle which particular this AC is traversing. So, if we see here, AC is this one which is at the bottommost position, and it is traversing some angle, that is a cone. We consider the small shaft segment here, and that shaft segment is traversing in a cone like this. So, this point is A. So, this line is making angle that is we obtained here, that is C prime by AC. Now, this is the angle. Now, what is the rate of change of this angle? That will be nu this divided by the time taken. So, nu into phi x. So, this is the rate of change of that particular angle. So, this is the angular velocity of the line AC during the motion of the disc. So, AC is having this particular angular velocity nu into phi x, and the direction of so we have obtained the angular velocity of the line AC, that is nu phi x. Now, we can able to get the angular momentum of the disc, because this particular disc is tilting about its diameter, this diameter. So, we need to consider the for angular momentum calculation ID, diametral mass moment of inertia, and we will be multiplying with this velocity which we obtained. So, angular momentum of this particular disc will be, so again I am drawing that figure. So, disc is here, disc is tilting about an axis which is diameter of the disc, and we will be having angular momentum in this direction as ID nu phi x. Okay. If we again relook into the direction of the angular momentum, this particular disc is tilting about diameter, let us say this is the axis. If we are looking from the top, the tilting direction is counterclockwise of the disc, and because of this the angular momentum is in the direction of this according to the right hand rule. So again I am repeating, the tilt of the disk when this particular disk is moving from time 0 to time dt is going inside the screen, and because of that the tilt about its diameter is taking place. If we look from the top, that particular disk is tilting in counterclockwise direction. So this particular angular momentum is in the upward direction. So once we obtain the angular momentum because of pure spin motion and because of the pure tilting whirling motion, now we can able to obtain what is the change in the angular momentum because of two motions. Now we can able to combine these two motions to get the general motion of the this particular disk. So we have this is the bearing axis, which is z axis. Let us say point A, which was the cone apex, is this one, and let us say this is the disk center line, and we had a angular momentum in this direction, which was in this particular direction, and there is another angular momentum, this one, which is having magnitude id nu phi x, and this angular momentum had magnitude ip omega. So here you can able to see this is the angular momentum due to the spin, and this is the angular momentum due to the whirling, which is whirling frequency nu. Now we will take the component of these vector or parallel to the bearing axis and perpendicular to it. So we know that this particular distance is y, and various angles we know because of the tilt of the disk. This is phi x, this angle is also phi x. So we have all this. So now let us say we are taking the component first parallel to z axis of this angular momentum. So ip omega cos phi x plus id nu phi x sin phi x. This because for thin disk case we know ip is equal to twice of the id. So if we use this in the above expression, and if we for small angle phi x, we can assume this is 1, and sin phi x is equal to phi x. If we assume, if you substitute these value in the above equation, we can able to write that expression as id 2 omega plus nu phi x square. So this is the net angular momentum which is acting along the direction of the bearing axis, z axis. Now perpendicular to the z axis, what is the component of these angular momentum? So this will be ip omega sin phi x. In this particular case, let us say y is positive in the downward direction. So we have the component of this is in the positive y direction, but component of this will be negative direction. So this will be id nu phi x, then cos phi x. Again, if we apply this simplification of the angle and we substitute ip is equal to twice id, this can be written as twice omega minus nu. So this is one equation, this is another. So these are the angular momentum which are acting along the direction of z axis and perpendicular to it. So now let us see these vectors separately. So the first vector, which is let us say this is the shaft center motion, which is nu. So, in this particular case we have the angular momentum which was parallel to the axis is this one. So, during motion this particular vector will always be along the z axis. So, if let us say if you consider other extreme here, again it will be same direction. Magnitude of these are not changing, and for this particular motion even the direction of this angular momentum will not change, always will be in the direction of z. If we see the second angular momentum, which was perpendicular to the bearing axis, this one, this particular vector during motion it will change position like this. So, if this is the C point and this is after delta time t C dash prime, then the direction of this particular angular momentum is changing, and because of this there will be change in the angular momentum, which will be C prime. And we know that this angle is nothing but nu into dt, because the whirling frequency is nu, and we have for delta time t this particular angle will be nu into delta t. So, you can able to see the change in the angular momentum, which is C prime, will be given as id phi x 2 omega minus nu into this angle nu dt. So, this is the change in angular momentum, and time rate of change of angular momentum we can able to get if we divide this expression by delta t. So, that will be this. So, basically this is nothing but the gyroscopic moment. So, this gyroscopic moment will be acting on the disc, and the direction of this gyroscopic moment we can able to get from this figure, that will be along the direction of C prime. That means in this particular case it will be into the screen, inside the screen. So, that means it will be acting, if we see on the screen, that will be acting clockwise direction. Onto the screen it will be acting clockwise direction according to the right hand rule C to C prime. So, this particular gyroscopic couple which we obtained is acting, that is the active couple which this particular disc will experience, and as we obtain, it is the direction of the gyroscopic moment is from C to C prime, that means into the screen, and this is the active couple. So, if we want to know what is the gyroscopic couple acting on the shaft due to the reaction, it will be opposite to that, that means it will be acting counterclockwise direction onto the shaft. So, if we summarize, we have now onto the shaft, if we remove the disc, the gyroscopic moment which we this is the reactive moment onto the shaft. So, this is opposite to what we got onto the disc, and so this will be basically outside the screen direction of this angular momentum, and value is, and the value is id 2 omega minus nu into nu. So this is and we have seen earlier, because of the linear motion, that means displacement y, we had net resultant centrifugal force Fy that was acting downward. This is the gyroscopic moment. So this is gyroscopic moment and this is the centrifugal force. If you remember, for the case of synchronous whirl, we had nu is equal to omega. That was the first lecture, and if we substitute this here, we will get the same expression as we got earlier. Only thing is, in this, I think one expression Vx is missing. So we'll get the same expression. If we substitute this, we'll get the gyroscopic moment as nu square Vx. So this is the gyroscopic moment which we got for the synchronous whirl condition, but now this was omega. So now we are considering the asynchronous condition. So the whirl frequency and the spin speeds are different. So now apart from this, we have this angle. If we project the tangent at the free end of the shaft, this is the phi x. So that means we need to relate basically this linear displacement or translatory displacement with the force and influence coefficients which we defined earlier. Why is it alpha 1 2, and similarly angular displacement will be given by this force with influence coefficients. So basically, if we want to see the definition of these influence coefficients, alpha 11 is nothing but the unit, the alpha 11 is the linear displacement for a unit force, keeping all other moments 0. So that means if we keep this moment 0, alpha 11 is equal to y if we are taking the Fy as 1. Similarly, alpha 12 is a linear displacement for unit moment when we keep all other forces 0. On the same lines, we can able to define alpha 21, that is a angular displacement for unit force keeping moment 0, and it is very clear that alpha 22 can be defined as angular displacement for unit moment and keeping all other forces equal to 0. So this is the definition of the influence coefficients, and these can be obtained from simple the bending of beam formulas. Like for cantilever beam case, we have these influence coefficients as L cube 3EI, and alpha 1 2 and alpha 2 are same, that is L square by 2EI, and alpha 22 is L by EI. So these influence coefficients, this is for the cantilever beam, in which the direction of the force is this one and moment is clockwise. So these have been derived based on this sign convention. You can see that the force is the same direction as this one, but the moment is opposite. So when we will use these expressions here, we need to keep these moments with minus sign, so that they are in line with the sign convention. So basically now we will be substituting this centrifugal force and this gyroscopic moment here, and we will be getting a homogeneous equation. So I am substituting those centrifugal force in this m omega, in this particular case, if we go back here, this centrifugal force is now, because is due to the pure whirling case. So, here there is a correction, this will be nu. Instead of omega, this will be nu, because in this particular case, if we again re-look into this, this is coming when we have pure rolling case, pure whirling. So, when the disk is coming here, its angular velocity is omega, and this is the y displacement. So, because of that, the centrifugal force at this particular extreme position will be downward acting, and the magnitude will be m nu omega square y. So, this will be nu square y plus alpha 1 2. We will be substituting the gyroscopic moment with minus sign to take care of the sign convention. This, then phi x to 1 m nu square y plus alpha 2 2. Here also we need to keep the minus sign. Now, we can able to see y term is here, y term is here, phi x is here, phi x is here. Now, we can able to rearrange this equation in a matrix form like this, where y and phi x I can able to write. So, here we will be having 1 alpha 1 1 m nu square, then here id alpha 1 2 nu 2 omega minus nu. Here we will be having, now I am keeping 1 2 and 2 1 same, because they always will be same. 1 plus alpha 2 2 id nu 2 omega minus nu. So, here I have kept alpha 1 2 is equal to alpha 2 1, because they are symmetric and they are equal. So, this is homogeneous equation. The one solution could be when both the displacements are 0, but there is a trivial solution. For non-trivial solution, we need to take the determinant of this equal to 0, and from this we will get a polynomial in terms of nu, and that polynomial can be written like this. So, this polynomial can be written like this. This will be 4th degree polynomial in terms of nu, which is whirl frequency, and in general obviously we expect 4 roots of these 4 solutions of this, but here so many parameters are involved. So, we will define some non-dimensional parameter like dimensionless frequency nu as nu bar as nu, and square root alpha 1 1 m, disk effect like this, elastic coupling between the linear motion and the angular motion, that is translatory motion and the angular motion like this. Then dimensionless speed I am defining like this. So, if we use this dimensionless parameter, this frequency equation will become relatively simpler. Here, apart from the nu bar, we have omega, there is a spin, there is speed parameter, coupling parameter alpha bar, and the disk parameter. So, we can able to solve this for, and we can get 4 roots, but let us take some special cases in which we can able to simplify this expressions. So, the case 1 in which we are considering, let us say id is 0, that means point mass we are considering, and for that mu will be 0, because id is related with mu. If you see substitute mu is equal to 0 here, you can see that mu is here. So, first we need to multiply mu to whole expression. So, this and this term will vanish. From the second term we will get 0 plus from third term we will get 0 minus alpha 1 bar nu bar square, and from this expression this will vanish because this will get multiplied by this mu. So, the last term will give us alpha bar minus 1 is equal to 0. So, you can able to see the solution of this will be nu bar is equal to plus minus 1, and we have defined the nu bar as nu alpha 1 1 omega. So, if we substitute this here, we see that the nu is plus minus 1 by alpha 1 1 m, and this alpha 1 1 is similar to the inverse of stiffness for cantilever beam case. So, this will be root k by m. So, you can able to see that this is standard stiffness divided by m as the frequency for when. So, when there is no disk effect, there is point mass, we will be getting the natural frequency which will be independent of the speed. In this particular polynomial, you can able to see the whirl frequency is dependent upon speeds. Some speed terms are there, but if this effect is not there, then this whirl frequency is independent of the speed. In the same expression, if we take another case 2, in which we have coupling parameter, that means the coupling between the linear motion and the angular motion is not there. In that particular case, we can able to simplify the previous polynomial, this one, by putting. So, I will take a second case in which we are having alpha bar is equal to 0, the coupling parameter is 0, elastic coupling. That means, in this particular case, we have in this particular case we when we are giving a displacement, linear displacement, the angular displacement is not taking place, and when we are giving a angular displacement, linear displacement is not taking place. This is a very special case. In generally, let us say if there is a simply supported beam and disk is at the middle. So, this during whirling will be having pure translatory motion, it will not tilt, and the same we can able to tilt without giving the linear displacement. So, other extreme will be this one. Other extreme will be this one, in which this will be tilting it about opposite direction. So, in this particular case, the disk will be tilting, but there is no translatory motion. In this particular case, there is a translatory motion, but there is no tilt. So, that is the particular special case. So, if we substitute in the previous polynomial and simplify, we will get a polynomial in the factorized form like this. So, after substituting alpha not equal to 0, this can be simplified like this. So, this is giving us first two as nu is equal to plus minus 1, and the second one is giving us expression, this one. So, you can able to see this is similar to the previous one, in which we have earlier the critical speed was the whirl frequency was like this, but in this particular case whirl frequency now it depends upon the spin speed of the shaft. So, if we try to plot this, if we plot, let us say omega bar here and nu bar here, and this is the 0. So, we will get corresponding to this horizontal line, because nu bar is, this is plus 1, and here is minus 1, corresponding to the first two roots. In the second equation, there is another parameter mu. For plotting purpose, we are assuming that mu is equal to, let us say, 1. So that means if this is mu is equal to 1, at the when this speed is 0, the nu bar is at this location, So basically, this is a, for this particular value only it will coincide here, and if we increase the speed, the frequency plot will be something like this, or if you decrease it, it will go like this. And similarly here, because there are positive and negative roots, so we will be getting this kind of curves. So this is one line, this is a horizontal line, and this is a curve, frequency curve. This is also a frequency curve. So you can able to see that we are getting at one particular omega, let us say, apart from the 0 spin speed. If we draw a vertical line, we are getting 4 intercept, 1, 2, 3, 4. But these 2 intercepts are, so there are 4 whirl frequency, but you can able to see that this is 1. So basically they are representing the same one. So for omega, when we are using the positive, we are getting this in 4 intercept. If we use the negative, let us say here, again we will get 4 intercepts, but those intercepts will be symmetric. That means these intercepts will be same as these ones, and these will be same as this one, and that is representing that when we are rotating the rotor in clockwise direction, we expect 4 critical speed, but if we rotate the same rotor in the anti-clockwise direction, we should get the same critical speed. So that is, it is representing, so either direction of the rotation, the critical speed of the system or the whirl frequency of the system should not change. So in this particular case, when we consider the coupling to be 0, we obtain the whirl frequency variation with respect to speed. In this particular case, if you want the critical speed, so for that particular case, as the critical speed condition is, if you remove this, the whirl frequency should be equal to the spin speed. So that means if we substitute this in this expression, nu bar is equal to omega bar, and we will solve for omega, then we will get omega bar is equal to omega bar plus minus omega bar square plus 1 by mu. And if we solve for omega, we can get the critical speed. And in this particular case, we will see that one of the critical speed, if we solve this for omega, will be minus 1 by mu. So that means in this particular plot, this nu is equal to omega line, if we draw, that is nothing but a 45 degree line. So if we draw this particular line here, this will intersect here, that will be corresponding to this critical speed. And similarly, if we draw this side, we will be having intercept here, here, and this solution which I am talking about is the intersection of this curve and this line. So because it is coming imaginary, so you will find that it will never intersect. So that means we will be having 4 critical speed, 1 this one, 2, 3, and 4th will be not feasible ones. This will be more clear once we will plot the the frequency for general case. So, now we have seen two cases. The third case is the general case. We are not assuming any particular special case. For that particular case, this frequency equation will be plotting it. Now, this frequency equation can be rearranged like this. So, for general case, we will take, let us say, cantilever beam. For that case, alpha bar, which we define as alpha 1 2, alpha 1 2 and alpha 1 1, alpha 2 2. So, if we substitute the previous influence coefficients which we expressed earlier, this will be a nice number, and let us say we are assuming mu is equal to 1. For this, the previous polynomial will be taking this particular form. And this can be solved for omega, because omega is linear term. So, this will give us expression like this. Now, we can generate for various values of omega bar, or now we can able to generate for various value of nu bar the value of omega bar. So, we can choose some value of this, we can, from this expression we can able to get the omega bar. So, there is no need to solve the polynomial. Directly for various value of omega bar we can able to get nu bar, we can able to get the omega bar, and this data we can able to plot it. So, this plot will look like this, in which this is the 0, omega bar is in the horizontal direction and nu bar is in the vertical direction, and we will be having 4 curves as we had previously, but they will be not horizontal. We will be having this kind of variations. Basically, if you draw a horizontal line, these two lines will be asymptotic to each other. Similarly, here if there is a horizontal line, we will be having like this, and so these are the 4 lines, 1, 2, 3, 4 lines which will be there. And if we draw nu is equal to omega line, this line will be something like this. This is a nu. So, we are interested in the spin speed, critical speed. So, intersections of this is a critical speed, one of the critical speed, and the upper curves are belonging to the forward whirl. So, this is one of the forward whirl critical speed. There is no intersection with the second curve. So, there will not be second forward critical speed, but if we draw another line which is nu bar is equal to minus omega bar, then we will be having 2 more critical speeds. This will be first critical speed backward whirl, this will be second critical speed backward whirl. So, in this particular case we are getting 2 backward whirl critical speed, but only 1 forward critical speed, other one, the second forward critical speed, is not feasible. And if we see the frequencies, these are the frequency lines, and at particular omega, that means if we draw a vertical line at any position, we are getting 4 intercepts to these frequency. So, they are because we had 4-degree polynomial. So, because of that these 4 values are coming. If we draw an identical line at negative omega, we will get 4 intercepts again, and they will be same as in this side. because if we rotate the rotor in clockwise or anti-clockwise, we should get the same whirl frequency. And in this particular case, this is called Campbell diagram. And this is very famous diagram for obtaining the critical speed of the rotor system, in which we plot the whirl frequency with the spin speed. What is the whirl frequency variation with respect to the spin speed? Okay, so I will conclude now. So today we saw a general motion of a cantilever beam with a rigid disc. So the motion was quite complicated because not only it has the translatory motion but also the tilting or wobbling motion. Apart from that, we took the complexity of the asynchronous whirl. That means the spin speed and the whirl frequencies were different, and because of that we had quite difficulty in understanding the especially the motion, and we followed the angular momentum approach to obtain the frequency equation. And we found that for this particular case, for a single disc case, we had 4 whirl frequency for a particular speed. So as we are changing the speed, the whirl frequencies are changing, and we try to find out at what speed these whirl frequencies become equal to the spin speed, and we could able to get 3 critical speed, 1 for the forward direction and 2 for the backward direction. The second forward was not feasible that we observed. So till now the gyroscopic effect we have analyzed using the quasi-static analysis. In the subsequent lecture, we will be analyzing this particular phenomena by a dynamic approach, in which we will be writing the governing equation, which will be time dependent. So till now we have not considered the gyroscopic effect based on the dynamic approach.